This is Circuits 101, a bit of an introduction to the foundational principles of circuits in Rec Room. A couple of quick procedural notes just when we get started. We are recording this and hope that it is of use to folks in the future. We are recording this on May 14th, 2024. We update Rec Room a lot. And so it is possible, if you're watching this in the future, possibly the far future, that some of the user interface or UX of creating things in Rec Room has changed. We are sorry, but the sort of core principles that we're going to talk about in this little presentation should remain true. Additionally, all of the demos that we're going to see are available in a room called Circuits 101 Demos. This is out live for anybody to go take a look at, hop in, take a clone of it, poke about as much as you want, in case that helps you understand what we're talking about. All right, let's get started. So circuits, or Circuits v2, or CV2 in its common abbreviation, is unsurprisingly the second iteration of user scripting in Rec Room. The first version was named Circuits v1, or at least has been posthumously named Circuits v1. It looked like this. Circuits v2, by contrast, looks like this. Most chips you'll see have this sort of appearance: dark gray header, light gray body, ports off the side. As CV2 has become effectively the way to program in Rec Room, it has sort of co-opted the name circuits. So if you hear somebody say circuits, they mean CV2. If for some reason someone needs to talk to you about CV1, they'll make it very explicit. Circuits v2 is a node-based programming language, right? It's a visual scripting language where you put down a bunch of these chips and you wire them together to construct programs. It is statically typed and event-driven. Those last two, if you're not a programmer, might not mean much to you right now. We'll talk about them in a little bit. All right, with that out of the way, as with most programming languages, the only way to begin is by beginning. So let's build our first program. Let's build a sort of stereotypical hello world. So here we go. We're in Rec Room. I'm going to pull out my maker pen and grab from my palette two things. One is a button, which we're just going to drop down here. And we'll see that that came along with a chip, and we'll talk more about that later. And then I'm going to grab one of these player show subtitle chips. I'm going to switch over to my connect tool, and I'm going to connect this pressed port on this chip that came with our button to the top port on player show subtitle. And then one last thing to do, I'm going to quickly tap this purple subtitle port with my connect tool and just enter the subtitle that we want to show, which in this case will be our standard hello world. And that's it, we're done. I can put my maker pen away, press the button, and there we go. Hello world circuit. We've built something with circuits. We'll talk about why that works and actually how that works in a minute, but first let's use it as an opportunity just to get some basic vocabulary down. So here's that circuit that we just built. These things, as you might have been able to gather, are called chips. All these things attached to those chips, those nodes, are what we call ports. And they are the things which carry data and execution around in circuits. The first thing you'll probably notice about those ports, they have a bunch of different colors. What's going on there? The colors are used to indicate the type of a port. All ports in circuits have a type, and that type indicates the kind of data that that port is responsible for moving around. So Booleans, these are true-false values, are colored red. Integers are colored green. Floats, decimal values, are light blue. Strings are purple, and so on. It's not actually a one-to-one mapping. We ran out of easily distinguishable colors at some point, and so a lot of our complex types are just colored yellow, but there are other ways with the maker pen to tell the type of a port. And types are important because they tell us which ports are able to be connected to each other. What do I mean by that? Well, in our example, all of the sort of data about the subtitle we wanted to show, we specified right on the ports of that chip with what we call default values. Right? We said the player that we want to show the subtitle to is the local player. The subtitle we want to show is just the string hello world. But it doesn't have to be this way. Ports are able to be connected together. This is how you attach chips and yield more complex behavior. Here's a slightly different version of that graph that we were just looking at. But in this case, instead of showing the string hello world as our subtitle, we've attached that port. We've connected that port to another chip, in this case, toString. And that toString chip is connected to the port on this board from the button for the player who pressed the button. Now, I will tell you, in this case, the toString chip will get you the name of the player who pressed the button. And so this is a circuit which, when you press that button, will show you your name. But what's important to notice is that our subtitle port, which is a string port, it's purple, is connected to another string port. Ports are only able to be connected to others with a compatible type, which in most cases means the same type. So string ports can be connected to string ports, but they can't be connected to int ports. You can't connect a bool port to a float port, and so on. Now, there's one other kind of port that you might have noticed, this sort of one with a unique shape on top, these orange ones. These are what we call exec ports. They're a little bit special. They don't carry data. They instead are used to denote the flow of execution around circuits. They tell us what is going to happen first, and then next, and then next. Okay, with that out of the way, I can introduce you to what is arguably the most important chip in all of circuits. This is not a joke, this is not a bit, it is extremely important. And it is the event receiver. It looks like this, and it's so important because in circuits, all execution begins from an event receiver. When you put this chip in your room, it sits there and does nothing. But you can configure it with the configure tool on your maker pen and set an event for it to listen to. We have a bunch of built-in events in recroom for creators to start using, things like your room loaded, or a player joined, or a player left. And this event receiver will sit there doing nothing until that event occurs, until, for example, a player joins a room, and then it will fire an exec signal out of its exec port, beginning execution of whatever comes after. Let us take a look at an example. Now, we haven't built up any real fundamental understanding of how circuits execute yet, but take a second, if you're watching this in the future, maybe pause. What do you think this circuit graph does? Just based on the information available to you. Take a moment, think about it. Player join subtitle with whatever the player's name is for about 3 seconds. And maybe you know how circuits work, maybe you don't. You might have been able to intuit this from just the text on the chips, and that's intentional, right? We hope that people can do that. And indeed, if we have another player join the room, here, let me invite in a friend. We've got Audzilla coming to join now. When she does, we would expect to see a subtitle pop up saying, hey, Audzilla joined. Excellent. All from our little circuit here. And maybe looking at this, that just makes sense to you. But let's dig in and get really specific about why this does that and how it does that. Let's learn how to read a circuit graph. Now, to do this, I'm going to introduce what are sort of the fundamental rules of the circuit's execution model. There's a couple of pieces here, and they all snap together at the end, so bear with me for just a couple of slides. First, let's talk about what it means for a node to execute. Right? If I say this chip is going to execute, what does that mean? When they execute, nodes do 3 things in this order always. They first read all of their data inputs from top to bottom. Then they do some piece of work, whatever that chip in particular is supposed to do. And then finally, they set all of their outputs. Always these 3, always in this order. Read inputs, do work, set outputs. That's what it means for a chip to execute. Here's an example. So our player shows subtitle chip from before. If I told you that this chip is executing, what it is going to do is first read all of its inputs. It's going to read in. What player should I show the subtitle to? What is the subtitle that I want to show? What is the duration of that subtitle? What is the priority of that subtitle? It will then do its work. It will display the subtitle on the screen, and then it will set all of its outputs. In this case, the show subtitle node doesn't have any data outputs, so it actually doesn't have to do anything for that step. Here's a different example. This is a raycast chip. It performs a raycast, a sort of standard gameplay physics operation. Fire a ray from a point in a direction, find out if it hits anything. When this chip executes, it will first read all of its inputs. It'll read the start position, direction, and maximum distance for a raycast. It will then do its work. It will perform that raycast. And then it will set the values of all of its outputs, a Boolean of whether or not it hit something, the player or object that it hit, the distance that it traveled before it struck it, and then the hit position and the normal vector of the surface that it hit. 3 steps in this order. That's what it means for a chip to execute. Now let's talk about when chips execute, right? What might cause a chip to do those 3 things? There's 2 cases we need to look at. For chips like this one, which have an exec port on them, has one of these orange ports, a chip will execute when it receives an exec signal on one of its inputs. Easy enough. For chips without exec ports, like this color to RGB chip or the raycast chip that we just saw, these chips will execute when any of their output ports are read. Say that one more time for clarity. A chip without exec ports will execute when any of its output ports are read. That's it. That is the fundamental execution model of circuits. That's pretty much everything you need to know to understand the majority of circuit graphs you'll look at. Let's see it in action. Here's that graph we were just looking at. What happens when a player joins, really specifically? Well, the first thing that happens, or the 0 thing that happens if you're a programmer, sorry, is that our event receiver receives the event of a player joining. It says, hey, a player has joined. and it sends out an exec signal across the wire that its exec port is connected to. That exec signal reaches our player show subtitle node. Now, player show subtitle is a node with an exec port. It just received an exec signal, so it will begin executing. And when a node executes, it will do three things. It will read its inputs, it will do its work, and then it will set its outputs. So player show subtitle first reads all of its inputs. It tries to read the player that it should show the subtitle to, and the value is right there for it, the local player. Done. Next, it will read the subtitle that it needs to show. Well, there's no value immediately accessible here, so we need to follow the wire to the other end to read the subtitle that we should show. Fine. So we go and we read the value from this result port on this string concat chip. But wait a second. String concat is a chip without exec ports, and we just attempted to read one of its outputs. That means that string concat needs to start executing. And so string concat will begin execution and do three things. It will read its inputs, it will do its work, and then it will set its outputs. So first, it will read its separator input. The value is right there. It is just a space. Done. Next, it will read the first value that it needs to concatenate. Well, that's plugged into a wire, or that port is attached to another over a wire, so it will read the value from the other side of the wire. So we will read the value of this results port on the toString chip. But the toString chip is a chip without exec ports, and we just attempted to read one of its outputs, so the toString chip will begin execution. And when a chip executes, it will first read all of its inputs, then do its work, and then set all of its outputs. I hope you're detecting a theme here. The toString chip will first read its value input. It's connected to a wire, so we need to look to the other end, and we will read the value of this player port on the event receiver. Now, the event receiver does have an exec port. So reading its outputs does not cause it to do anything. We just read the value that's sitting there, which is the player who joined the room. So toString finishes reading in the value of the player who joined. toString has now finished reading all of its inputs, so it will now do its work. It will convert that player to a string, to text, by, in this case, taking that player's display name, and it will then set its outputs. It'll set the value of that result port, at which point toString has finished execution. Why was toString executing again? Oh, right. We got here because we were reading this second input port from string concat, so that can now finish. We can read in the name of the player who joined the room. String concat will then read its last input port, the string joined with an exclamation mark at the end. It will do its work. It will concatenate those strings together with a space in the middle, and it will set its outputs. It will set the output of this result port, and then string concat has finished execution. Why was that chip executing in the first place? Oh, right. We were reading the inputs for the player show subtitle node. And so player show subtitle can now finally finish reading the input of its subtitle port. Done. It is player name joined. It can then read the duration that we want to show the subtitle for and the priority of that subtitle, at which point player show subtitle has finished reading its inputs. It will do its work by showing the subtitle on screen, and then it will set all of its outputs, of which there are none. And it will finish execution. And it will then send an exec signal out of its exec port to whatever is connected down the line, which in this case is nothing, and so we are done. This is the fundamental execution model of circuits, and you can use it to read the vast majority of graphs you'll come across. A way that I like to put it is that we can read exec left to right, data right to left. Starting from your event receiver, we can follow an exec wire left to right to the next chip, and then read from right to left its data ports to see where that data comes from. Hopefully that's making sense. With that out of the way, we can now talk about some circuits features that you'll encounter in the language, some things that allow you to express more complex ideas. The first of these are variables, hopefully not a surprise to anybody who's done any programming before. Store a value, retrieve it later. Variables come in the form of chips like this. We've got one for each of our various types. So this is an int variable. You can tell because it says int variable on it, but also because it has two green integer ports. Float variables have float ports, string variables have string ports, and so on. And this chip behaves just like any other. It has an exec port. So if it were to receive an exec signal, it would first read its input, do its work, which in this case is saving that value for later, and then it would set its output, and execution would continue. Now, as a nicety, you can use the configure tool on your maker pen to rename variables to be something useful, hopefully. And if you have multiple variable chips in the same room with the same name, they are the same variable. This is good for two reasons. One, just an expressiveness thing. There's actually a couple of cases that you couldn't build a program without that. And two, it's nice to not have to draw a wire a mile across your room because your variable chip was on the other side, when you could just put down another copy of a variable with the same name. All right, here's a fun example. Again, take a moment. What do you think this does? Pause maybe if you're watching this. It's going to count up the button presses. This is a counter circuit. When I press this button for the first time, we'll see a subtitle that says 1, and then 2, and then 3, and so on. And if we really analyze this, we can understand why, using the same strategy we did before. Press the button triggers execution of the int variable, which needs to read its inputs. To do that, it will read from the add chip. The add chip first needs to read from the current value of the int variable, which, when the room loads up, is 0. So this will add 0 to 1, get 1, and that will be used as the value we are going to set into the variable. Then execution continues, exec left to right, onto the show subtitle node, which will show the current value of the variable. This little loopback thing can be confusing to people, so in case it helps, this is precisely the same graph. Excuse me. Because these two variable chips have the same name. Maybe that makes it clearer. Maybe it doesn't. Moving on. Another feature you'll find in circuits, events. We've talked about these already, right? We've seen the event receiver, the arguably most important chip in all of circuits. I mentioned before we have a lot of built-in events for players to listen to, things like player joined. But we also give creators the ability to define their own events for whatever they need with a chip called an event definition, which can be renamed and customized as seen fit. So I've created an event here called cow jumped over the moon, which will happen, presumably, when a cow jumps over the moon. But something else from before that you might have noticed is that our event receiver for player joined didn't just fire an exec signal. It came with a piece of data. It didn't just say a player has joined. It said, hey, a player has joined, and this is the player that just joined. And creators can do this too. They can attach what we call properties to events. In this case, I've attached a property called number of cows, which is an integer, green, and the phase of the moon, which is a string, purple. And so when this event gets sent, it will get sent with two pieces of data, a number of cows and a moon phase. And this can be sent using a chip called an event sender, the counterpart to our event receiver from before. It looks like this, and using the configure tool on your maker pen, you can choose what event it should send. You're not allowed to send the player joined event, for example, but creator-defined events can be sent from any event sender in the room. And when that event gets sent, it will then be received, heard by any event receivers in the room, which are tuned to listen to that event. And so here we have sort of a simple example where our button will trigger execution of our event sender, which is going to send the event that a cow jumped over the moon, in particular with 87 cows and a waiting gibbous. That event will then be received by this event receiver, which will trigger execution of the rest of our circuit graph. In this case, just showing a subtitle with that information. And we can see that that works here. 87 cows jumped over a waiting gibbous. Great. Now you might be looking at this and thinking, well, why did you bother with the event? Seems to me like you could have just wired the output of our button directly into our show subtitle node. And you're right. In this case, that would have been equivalent. But events are a useful tool both for organization and for expressiveness. There are instances where maybe you want to reuse this piece of logic, right? Maybe there are several things in a room which could cause a cow to jump over the moon. And instead of having to copy the rest of your chips around, you can rig them up to an event receiver and then send the event from 100 places if you need to. It can also be nice for sending an event in one physical location and receiving it in another physical location so that you don't have wires running a mile across your room. But that's just for organization. Okay, that's events. Lastly, in our little list of basic circuits features, let's talk about circuit boards. This is a fun chip. It does nothing. Instead, it is a container for other chips. This is a chip that you put chips inside of. This is a nice way for creators to sort of encapsulate pieces of logic that they don't want or need to be exposed outwards. It gives them a slight notion of scope, although I use that term very carefully. It has a bit of a baggage for those of us who have programmed in textual languages before. Circuits doesn't have all of the concepts of scope that you get from a more traditional language. So I use that term a little bit carefully. We can see what one of these looks like over here. Here is a circuit board that I just spawned out of the maker pen and saved into this room, so it is empty. And we can use the edit tool on our maker pen to open it up and see what's inside. There's nothing. There's just these two things that we call an in bus and an out bus. But we can change that. We can configure this chip and add ports to it. So let's add an input port that is, I don't know, maybe a bool, and an output port that is, say, a float. And we will see on our chip, on our circuit board, has appeared a bool input and a float output. And if we edit into this board, we will see that our in bus has gained a bool port, and our out bus has gained a float port. The in bus and the out bus serve as the sort of points of entry and exit from outside to inside the circuit board, the way data and execution moves sort of through the barrier of the circuit board. As an example, I have crafted this one down here, which I've renamed to same assign. This is a circuit board that has 2 integer inputs and a single bool output, and it will tell you whether both numbers have the same sign, right? If they're both positive or both negative. You can see here they're set to 42 and 87, which are, of course, the same sign. But if we changed one of these to be negative 42, now it is false. And the beauty of this is that you don't have to know what's going on inside. But you can, if you wanted, edit into it and see the collection of chips that are driving that piece of logic. That's circuit boards. That's all for the sort of fundamentals of circuits itself as a language. Now let's talk a little bit about rec room interoperability, right? All that stuff is fantastic. How do creators use it to build things in rec room and interact with the rest of rec room's systems, right? We see all sorts of creative, expressive rooms, and they do more than just checking if 2 numbers are the same sign. 2 ways that they do this. The first are something that we call object boards, and you've seen these already. When we spawned a button earlier, you noticed it came along with this chip. That's something we call an object board, which conceptually is really just a circuit board that belongs to or is associated with a specific rec room object. And we show you that too. In this case, if you have a button selected, you see this little ant line, which shows you, hey, this object board belongs to this button. And it has on it a couple of ports for what we think are common use cases that people might want out of an object board. So in the case of a button, an exec output for when that button is pressed and an exec output for when that button is released. So if a creator doesn't want or need some of that functionality, they can remove or change it as necessary. And this is the one for the button, but we've got tons of components that let creators do a whole wide variety of things. We've got trigger volumes to detect when players or objects enter and exit a particular region, pistons and rotators to move things around, world space text, point and spotlights, audio players for sound effects and user recorded audio, trigger gun handles, sword handles, swing handles to let people hold things in a variety of creative ways, animation controllers for keyframe animation, and the list goes on. Now, one thing you might notice about these object boards is that they've got this like extra port hanging out on the header section, kind of above everything else, in that dark gray section. They've got a yellow port there. What's going on there? This is what we call a self port. It's a little bit special. That port gives you a reference to the object to which the board belongs. I'll say that one more time. The self port gives you a reference to the object to which the board belongs. And so in this case, this little self port on the top of the button's object board will give you a reference to that button. Not all buttons, not the concept of a button in general, but that specific button. Why would you want that? Well, because the other way that creators can have circuits interact with rec room objects is through what we call interop nodes. These are nodes that are designed to operate on specific objects, like in the case of these 3 up top here: piston set speed, light set intensity, audio player set volume, or in some cases, operate on players like these 3 down at the bottom: set position, go to room, for when people are building multi-sub-room or multi-room experiences, and things like setting camera shake. And those 3 on the top, which operate on objects, let's take piston set speed, for example, have a target port. That chip needs to know, oh, you're setting the speed of a piston. Which piston? And where might you wire that port to? The self port on an object board. Here's an example. We have here the button set text chip. This button has some text on it. It says push me. But this chip allows you to dynamically set what that text is. And you'll see that we've wired up the target port on this chip. Hey, what button would we like to set the text on? That one, the one to which this object board belongs. And in this case, we're just setting it to be the name of the player who pressed the button. And we can see that work here. Hopefully that all makes sense. And so these are kind of the two main ways in which creators can use circuits to interact with Rec Room objects. You've got object boards and you've got these interop nodes. Except those aren't really two separate things. You see, I said before that object boards are circuit boards associated with an object, and I meant it. They are circuit boards. And like any circuit board, you can open it up and see what's inside. And in there, you will just find interop nodes. These things are just circuit boards. They have this little bit of special behavior with the self port, but other than that, are standard circuit graphs that abide by the same rules we've seen before. And creators can open these up and do whatever. They can delete all of these chips if they like. They can add completely custom functionality and make that object board do anything they want. One other quick note with this. You might have noticed that our object board for our button has these exec ports. And you might have been thinking, hey, wait a minute, didn't you say that all execution in circuits begins from an event receiver? That doesn't look like an event receiver. If you had that thought, good catch. But I wasn't lying. Inside this object board are event receivers. It really is just the same set of fundamental rules again and again. We build them up into something more complex, but it's the same rules at the base. Okay. Now let's move on to something really exciting. It's time for everybody's favorite game. What do you think this circuit does? Take a sec, stare at it. When a player joins the room, we will first generate a random integer between 0 and 99 inclusive. Then we will show a subtitle, where the message of the subtitle is the random integer converted to a string, converted to text. Okay, easy. So we would expect when a player joins, we'll see a random number between 0 and 99 appear on our screens. Let's test it out. I'm going to invite Audzilla back to this room. And as soon as she joins, we should see a random number appear on our screen. 45. Nice. Audzilla, you got 45? Nope. What'd you get? 28. Audzilla got 28. What's going on here? This pulls back the veil of multiplayer games, the great illusion of multiplayer games. We make this presentation to our players, as most multiplayer games do, that they are existing in a shared space with their friends. This is a lie. The game client is running on each of their machines independently. There is a representation of their avatar on each of those computers. And Rec Room in the back is working very hard to keep those representations in sync. And Circuits shows this to players. It makes it clear that you are in a different application, different instance of an application than somebody else. And this is probably not a revelation to those of us who work on games. But to our creators who maybe don't work in games, or maybe are kids still in school, this is a new idea and something that's not necessarily intuitive. For the first time, they have to think about networking. So let's do so now. All Circuits execution is local. This is a bold statement, but it's true. No asterisks, no special cases. Circuits execution is local. Any code you write, like generating a random number, will run on an individual player's machine. And this means that Circuits gives creators the power and the responsibility to manage synchronized and local state. If you wanted to build a room where a random number pops up when somebody joins the room, but it's the same number for everyone, you've got to construct that yourself. But Circuits gives you the tools to do that. And actually, it's nothing we haven't seen before. We've already seen these. Event senders, which we used previously to just send an event to an event receiver elsewhere in the room. The keen-eyed among you may have noticed that when configuring that, there was not just a drop-down menu for what event should we send, but also a drop-down for who we should send it to. The default is local, to send it to yourself, but you can set it to go to everybody else, or everyone in the room, or a specific player. So events are not just for organization, though they're great for that. They are also for managing networking, for telling specific players to run specific pieces of code. Variables, the same variables that we saw before, have a toggle in their config menu to make them synced. And when you turn that on, if anybody sets the value of that variable, Circuits will take responsibility for propagating that update out to all of the other clients, so everybody sees the same value. Now, it's worth noting here, we don't completely throw creators into the deep end. Most of the Rec Room components that you can pull out, things like buttons, lights, text, all of these, kind of work out of the box the way you'd expect them to. those Rec Room components that have a visual representation anyway, like a light, let's say, have a synced toggle in their own config menu, which is on by default, so that everyone will see the light on or off together. They will see it with the same color and the same intensity. But if a creator wants to, they can turn that off, and they can take responsibility for managing the local state of that light on everybody's clients. And people can use this to great effect, to create some very deep and individualized experiences. Additionally, physical objects, things that sort of players can directly physically interact with, things like geometry or maybe a basketball, are always synced, at least for now, though we have occasionally discussed relaxing this constraint. This is to maintain this idea of sort of shared perception. We think it would be odd if two people were standing in a room and someone said, look at that basketball, and somebody else said, what basketball? These are really the essential principles of circuits, and is kind of everything you need to know to get started. Hopefully that removes some of the, I don't know, apprehension or fear around jumping in. With just these simple principles, we've used circuits to great effect, right? Our last RRO, Make It to Midnight, was built entirely with circuits. All of its game logic runs inside of circuits, all of its networking. The next RRO that we're working on, My Little Monsters, also built with circuits. We're even using it right now in rooms too. All of the locomotion of a player, the fact that when you push your joystick forward or press W on your keyboard, the fact that you move forward is driven by circuits. This is the custom locomotion graph, which defines how movement works. Disconnect this and you can't move in a room anymore. Right? Circuits is very powerful. Creators have used it to build tons of experiences of varying levels of complexity, up to and including building their own programming language, which sits on top of circuits. No, I'm not kidding. Go check this room out. It's ridiculous. And that's it. That's the fundamentals of circuits. Thanks, everybody.